Our next speaker is Omkar Bate, who has recently joined us in the Observable Working Group, Observable Universe Working Group of the Cosmic AI Institute as a Cosmic AI Fellow. And Omkar is going to talk about using AI for imaging radio interferometric data.
Sorry, my
Thanks. I would like to thank the organizers for giving me an opportunity to do my work. So I want to talk about some work I did during my previous postdoc at the University of Geneva on AI-driven radio image reconstruction. So this work was done as part of the AstroSignals collaboration at the University of Geneva, which involved people from astronomy and the computer science background. So we came together to develop like new tools and techniques for radio access. So just to give like a background for people who are not familiar with imaging in radio astronomy. So in radio astronomy, we have these interferometers, and they don't measure the sky directly, but instead with radio interferometers, we measure the Fourier transform of the sky, which is also termed as the UV plane, and the quantities we measure are the visibilities. However, the issue is that we couldn't simply inverse Fourier transform it because there's a lot of missing information in this Fourier plane. So because of various reasons, we cannot completely sample this plane. So because of this missing information, there's a lot of artifacts that would be produced in the recovered image, which itself is termed as a dirty image. So here's an image. Here's an example of such a true sky, and if you sort of have such a sampling, there'll be all kinds of artifacts around here. And this, on top of that, there will be like a noise from the instruments and all as well, right? So the problem is that fundamentally, imaging in radio astronomy is an ill-posed problem because of this missing information. What happens is that basically for any given dirty image or the sampling, there are multiple sky models that are consistent. So there's more than one solution in terms of this reconstruction. But radio astronomers have first found like a solution to that, termed as radio image deconvolution, using what is called as the clean algorithm. So clean essentially iteratively creates a model of the sky using a set of components, usually a bunch of point sources or a bunch of Gaussians of different scales. Want to model the diffuse emission. And this traditional sort of approach is basically you have your visibilities, you get a dirty image, do the clean on that, get the clean image, and then you can sort of do all your downstream tasks, things like source localization, flux estimation, and all kinds of science that you do, right? The problem is that still clean, although it gives you like an image, but it doesn't fundamentally solve the ill-posed nature of image reconstruction. It kind of gives you a solution, but there are there are various other solutions which are also possible. And on the practical sense, clean does not scale very well to large data sets. So as we enter sort of the era of next generation radio telescopes like the ngVLA, SK, these techniques will be heavily challenged. So this was our motivation to sort of develop AI-based tools to replace these traditional methods. So there are sort of two questions we ask. In the first case, can we essentially skip this entire process of imaging and deconvolution? So a radio interferometer measures the visibilities, and can we directly do this downstream task, for example, source localization, directly on the UV plane using sort of a pre-trained AI model, right? And to go a step further, can we use these modern generative AI models, for example, specifically we tried denoising diffusion model to address this ill-posed nature of image reconstruction. So using these sort of stochastic and generative models, we can actually come up with multiple solutions which are consistent with your observations. To answer that, sort of to test these ideas, we simulated large amounts of ALMA data, and to sort of keep our problem simple, we were focused on sort of a specific science case which was targeted for high redshift galaxy science in the deep extragalactic cosmos field. So, but those are details which are not really important right now here. And I'll very quickly go through the simulation details. So basically, since we were targeting high redshift galaxies, much of our sort of interesting or the science targets are point sources or sort of simple sources. So this is a typical example of the sky model. And this is the corresponding dirty image in the simulations. And what we did is we had multiple pointings in the cosmos field, about 10,000 or so, in total consisting of 27,000 sources in each of these independent pointings. And we also have based on the simulations, all kinds of data products like the true sky model, the UV data, the visibilities, the true source catalog, and the dirty and clean images. So you can use all of that to train our AI model, and that's where I would like to move next. So in the first step, what we try to do is, as I was mentioning, whether we wanted to see if we can sort of detect this source locations directly from the UV visibility. So kind of created such an architecture where the input was the visibilities, and based on, there are like multiple stages in this AI model, which eventually gives us this kind of a sky model, which tells us where the sources are. In some sense, what we're trying to do here by these multiple stages is to effectively improve our output from this model. So if you look at from our stage one, this is the true sky, and this is what it predicts from our stage one, which is basically a fully connected layer. There are still some artifacts left over, but then what we also have is another autoencoder layer, which kind of tries to denoise this and remove some of these artifacts to further improve it. What it finally gives us is actually a binary output. So we can't really, it's not really an image of the sky, but more like it helps us to tell us where the sources are. So it's mainly focused on source localization. So this is for one example, but I want to show how it performs on our entire test data sample. In order to check this kind of a performance, what we try to do is we try to basically tune the hyperparameters so that the purity, or what people from AI background are used to hearing as a precision, is maximized across all the models. And we also compare our model with the classical approach, which is of source localization or source detection using PyBDSF. So even there, we tune the parameters so that we have the best purity in our detections. And then we compare the completeness or recall as a function of signal to noise ratio of the sources. So using traditional methods, what we expect is as we go to low signal to noise ratio, if you look at the blue lines here, the completeness essentially reduces. You end up missing faint sources, which is typically expected, right? What we see with our model is that compared to the traditional approach, it's outperforming these at low signal to noise ratio. So it's very well tuned towards detecting faint sources. So for instance, already SNR of 3, you see that you are still recovering like 80% of the sources. So that's what's more is that the AI model is very fast. So compared to the traditional clean and PyBDSF approach, our model is about factor of 30 faster. So you can very quickly sort of tell where the sources are just from the visibilities, right? So just to tell you very quickly, what are some of the sort of use cases? Such kind of techniques, as I said, is ideally suited for detecting faint sources. So there's a lot of potential to sort of for new discoveries, right? As you go to the faint sky, you can sort of start to identify, detect new kinds of sources. Additionally, this technique can provide you priors to the classical clean approach itself. So it can tell you where the sources are located very fast, and that can help you to reduce the clean iterations. So this can expedite the traditional approaches as well. And if you can generalize it to sort of all kinds of sky at different frequencies, like low frequency and so on, complex image structure, we can actually very quickly like produce these catalogs of source of the locations of the sources. So this can be very useful for transient science. Like you don't have to sit and image the entire sky. Just from the visibilities, you can quickly identify the sources. So I want to spend some time on the next approach, which is even more interesting, is to not just to identify the sources itself, but to do the complete image reconstruction. And to do this, we used a stochastic model, specifically the denoising diffusion probabilistic model. And what it does in very simple terms is that when we during the training stage, basically we take the true sky, and this model progressively, using a diffusion process, will progressively add noise into the data, such that towards the end you end up with a noise model which is effectively indistinguishable from pure noise, right? And then there's a reverse process, which is the inverse process is of the denoising process, where we use a simple UNet to progressively denoise this noise model to produce the true sky, and then and during this process we actually give the dirty image as a conditioning, so that it doesn't generate like arbitrary sky, but it sort of is physically motivated from based on what the sort of dirty image is actually. So in the DDPM approach, this is how you would sort of apply it in the real case. So you start with and this is the inference stage now. So you start with some model noise, and you'll have your dirty image from your observations. In our case, we had simulated dirty images, but in reality, you will have your own sort of from the observations. And you feed it to this DDPM model, it will generate a sky model for you, which is, because of the conditioning from the dirty image, it's sort of consistent with what you would expect actually. Yeah. So what is the other thing that is sort of interesting with this model is that it's a bit hard to see here, but because of the stochastic nature of the model, every time you feed it, you'll end up sort of having slightly different realization of the sky. So it's better to see on the screen here, but basically this is an example of the dirty image, and this is sort of the various realizations from this dirty image, and you can see that it's largely consistent across the various iterations. But in some cases, like here, you can see that there is a faint source which ends up popping up, not in all the cases, but only in a few cases. And if you look into the true sky model, that source there is actually a very faint source. So this also allows us to add in the stochasticity in the sky model, and gives us like an uncertainty or a reliability on the image reconstruction. So based on the sort of a variance of the from these realizations, we can actually associate a reliability score. We can also give like an uncertainty on the flux estimation. So just to quickly compare from the previous case, this model actually even outperforms the previous model that I showed in terms of completeness versus SNR. And what is also important is we are also able to recover the flux. So this is the flux recovery plot from our true versus DDPM-based recovered plot. And the uncertainties here are actually from the various realizations. So that's something sort of a step above just a single sort of a sky model reconstruction. Finally, I just want to spend like a slide on the kind of project that we plan to do as the observational universe group here. So the first task that we plan to do here is to do anomaly detection for radio calibration. Specifically, like we want to train like a neural network to automatically identify problematic calibration table, problematic visibilities, and so on, which will help to sort of expedite the existing calibration pipelines with close to like minimal human intervention. So that's the aim. And to do that, we are currently developing an autoencoder to learn what is good calibrations across a large set of well-calibrated ALMA data. And then the idea would be to use this autoencoder to use it like an anomaly detector. And the main challenge in such an exercise is to be able to generalize the model across a large set of observing conditions, various instrument effects, the sort of large data dimension of visibility, and the different dynamic range in the signal to noise ratio of the sources and so on. So we are currently the ALMA archive helps a lot. So we are sort of collecting the data and preparing the data for this modeling. But it will be important to see how this works on things on data that it has never seen before and so on new data. And we expect to have some results next year, sometime in the middle of next year or so. The other project that we are also doing is on hyperspectral tube image segmentation to basically do automatic image segmentation and masking. This is again to expedite and increase the efficiency of creating science-ready data products. So I just want to sort of just want to leave here with the summary that AI shows a lot of promise, particularly at efficiently and accurately detecting faint sources, and they can detect sources directly from the UV plane and the dirty images, so we need not have to do clean necessarily. And DDPM and this kind of class of generative models shows the potential to even perform the entire image reconstruction. And this, this highlights like the potential to deliver like robust and efficient solutions for imaging in the era of next generation radio astronomy.
Great, thanks, Omkar. Okay, we have time for a couple of questions. We have one online. Shunwan, do you want to unmute and ask your question?
Yeah, so very interesting talk. So for your second part, the diffusion model, you show that if you have point sources, you can reconstruct the point sources from the node with a diffusion model. My question is that if we have some other like pro-parent disk images is not a point source, do we need to first train the model on some similar disk images and then do the reconstruction, or your model is generally applicable to any kind of images, any morphology in the images? Thank you.
In its current form, it is not, because we are focusing on specific science case and also wanted to experiment how these models work. But I don't see why, like, if you put that in the training data, we can actually also generate various other morphologies like disks, rings, and so on. But in the current form, it is not trained for that.
If you want to stop the screen share, we have time for one quick question in the room.
One back.
Sorry, I'll take this one back here. Speaking of that,
I was wondering, like in your source localization model, if you do not detect a source, can you provide physically meaningful upper limits on how bright the source is?
If you do not detect, we can't, right? Like, there's nothing. But what you can do essentially is like you have the model from the DDPM. You can construct a residual image and then sort of use the noise in that region to put an upper limit on it. Yeah, so which is what you standard like typically also do in clean and stuff.